Hello. In several of the examples that you just saw Candace and Ann work, they used a different scale on the horizontal axis from the scale that they used on their vertical axis. This use of different scales on the horizontal and vertical axis is technically always an okay thing to do. What I'm going to discuss with you is the fact that sometimes, though, there are ramifications of using a mismatched scale that you need to watch out for. I'm also going to discuss how important it is that you can carefully read the scale on any pre-printed graph. The big lesson today is how important it is that you include a scale on any graph that you produce, and how important it is that you read the scale on any graph that is given to you. I'm going to begin with a little section I like to call slippery slope. And I'm going to conclude with an example where we're discussing broken scales. What is it that makes a slippery slope? It's a change in scale. One of the pairs of blue and red lines is perpendicular. There's a pair in figure 1 and there's a pair in figure 2. Which pair is perpendicular? Well, you might be thinking, what a silly question. Obviously, it's the pair in figure 2. And you know what? If there was no axis system here, you'd be absolutely correct. Given the conditions of the problem, the pair of lines in figure 2 is the pair of perpendicular lines. You might be surprised to find out, though, that if we add an axis back to each figure, the question is a little bit more complicated than it seems. Let's begin by considering what the answer to the question is if we have an equal scale on the x and y axes. Since without the axis system, the pair on the right was the pair of perpendicular lines, let's check it out if that's still true when we have an equal scale on the x and y axis. Let's recall that two lines are perpendicular if and only if the product of their slopes is -1, remembering that this is provided that neither line is vertical. Let's see what the slopes of our lines are in figure 2. In figure 2, on the blue line, I have the point 2, 3. I did consider the scale before I said that this was the point 2, 3. I also see that I have a scale of 1 on both the horizontal axis and the vertical axis. So when I move from the point 2, 3 to this point right here, since I'm rising one box and running to the right one box, that would be a rise of 1, a run of 1, everything's 1. 1 over 1 is 1. The slope of the blue line is 1. How about the red line? Well, on the red line, if I move from this point to this point, I go down one box, that's a rise of -1. I go right one box, that's a run of +1. A rise over run is -1 over 1, which simplifies to -1. The slope of the red line is -1. Is the product of their slopes of these two lines -1? Last time I checked, -1 times 1 results in a product of -1. So with this graph that has equal scales on the x and y axes, the two lines are still perpendicular. Let's see what happens if we have a different scale on the y-axis than on the x-axis. Let's consider each graph separately. What I've done is I've gone ahead and indicated in the table a couple of points on the red line and a couple of points on the blue line. On the red line, we have the point 0, 10. We also have the point 2, 6. 2, 6 is the point of intersection between the two lines, so 2, 6 is also on the blue line. On the blue line, we also have the point 0, 2. Let's use all these points to figure out what the slopes on the two lines are. Looking at the points I have in the red columns, from 0 to 2, that's a run of 2. From 10 to 6, that's a rise of -4. Y is decreasing by 4. So the slope of the red line is -4 over +2, which simplifies to -2. How about the blue line? From the first point to the second point, the run is +2, the rise is +4. So the slope of the blue line is +4 over +2, which is +2. If these two lines were really perpendicular, the slope of the red line multiplied by the slope of the blue line would result in -1. Well, what happens when we multiply -2 by 2? Or, more importantly, what doesn't happen? And what doesn't happen is that we do not get a product of -1. So these two lines, in a sense, are not perpendicular. By using a mismatched scale on our x and y axis, we have created the appearance of perpendicularity between two lines that do not really meet at a right angle if they're drawn on an axis system with equal scales. What created this problem? Well, the creation of the problem can be thought of like this. Let's see how far it is from 0 to 6 on the y-axis. I've indicated that with this little green dumbbell-looking object. Let's see how long it takes to get from 0 to 6 on the x-axis. What I'm going to do is I'm going to duplicate the dumbbell 2 times to explicitly illustrate that it takes twice as long to get from 0 to 6 on the x-axis as it takes to go that distance along the y-axis. So in a sense, what I've done is I've stretched the x-axis by a factor of 2. That has also changed the orientation of the two lines. Let's squish the x-axis back so that it takes the same distance to get from 0 to 6 along the x-axis as it takes to get from 0 to 6 on the y-axis. So what I'm going to do is I'm going to segue to a new graph so that along the x-axis, the point 6 is here rather than here. And let's see what the ramifications are on our two plotted lines. Well, something very positive just happened. Our lines no longer look perpendicular. We do not have a false visualization of two perpendicular lines when we have equal scales on our x and y axes. Let's go back to figure 1. These lines don't look the least bit perpendicular, but let's notice that we don't have an equal scale on our x and y axis. The scale on the x-axis is 1, the scale on the y-axis is 2. So we might be visually fooled into thinking that the lines aren't perpendicular when in fact they are. Let's check out the slopes. I have the point 2, 6 on the blue line. I also have this point on the blue line. The rise between those 2 points is 1 box, and the run between those 2 points is also 1 box. So you might think the slope is 1 over 1. You'd be wrong, because you haven't yet considered the scale. When I affect a rise of 1 box, since the vertical scale is 2, that's actually a rise of 2. When I affect a run of 1 box, since the scale on the x-axis, the horizontal axis, is 1, that is a run of 1. So all put together, the slope of the blue line is 2 over 1, which is 2. How about the red line? Well, here's 1 point on the red line. Here's a second point on the red line. What's the rise over run to get between those 2 points? Well, I need to go down 1 box. Down 1 box with a scale of 2 on the vertical axis is a rise of -2. Then I need to go right 1, 2, 3, 4 boxes. A run of rightward 4 boxes when you have a scale of 1 is 4. So we have a rise of -2, a run of 4. So what's the slope? The slope is the rise, which was -2, over the run, which is +4. That simplifies to -1/2. Let's check out the product of these two slopes. The slope of the blue line multiplied by the slope of the red line is 2 multiplied by -1/2, which is -1. Holy smokes, these lines are perpendicular. They sure don't look perpendicular. What's wrong with the picture? Well, in one sense, there's nothing wrong with the picture, except that we're creating an illusion where two lines that should be perpendicular don't appear perpendicular. How can we make the lines appear perpendicular? By using equal scales on the x and y axis. I have the same scale that I had in the last example. So the problem here is that it's taking twice as long to get from 0 to 6 on the x-axis as it takes to get from 0 to 6 on the y-axis. One way I could fix this problem is I could just squish the graph horizontally by a factor of 2. So I think that's what I'm going to do this time. So let's squish. So sure enough, the lines now look perpendicular. Let's verify that on our squished up graph, we do have an equal distance from 0 to 6 on both of the axes. So here's our distance from 0 to 6 along the y-axis. Let's duplicate that, rotate it 90 degrees, and see that yes, indeed, we do have an equal distance from 0 to 6 on the x-axis. Now you might be thinking, actually, it's kind of a little bit difficult to read these numbers on our squished up graph, and I think I agree with you. So I went ahead and kind of stretched this graph out again, maintaining my equal scale so that we really can verify that we have equal scale on each of the axes. The scale on both the vertical and horizontal axis is now 2. It takes the same distance to get from 0 to 6 along each axis. And when we graph these perpendicular lines on an axis system that has equal scale, by golly, the lines actually look perpendicular. That's a good thing. Let's consider another place where mismatched scales might create an illusion, an appearance that is in fact not borne out in reality. Let's look at this line graphed on a YT axis system. The question is, what is the slope of the line shown in figure 3? You know what the answer is? I have no idea, because there's no scale. Now, you might be thinking, well, gee whiz, it looks like the line is cutting halfway into the first and third quadrant. And one ramification of this would be that the rise and run from one point to the next must be equal. I can actually demonstrate that you're right. That is, in fact, true. I've introduced a rise of yay long. I'm duplicating and moving it into a run, and sure enough, when I effect a rise and a run of equal length, I do move from one point on the line to another point on the line. Now you might think rise over same rise, which is acting as the run, always reduces to 1. That is a true statement, but we don't know that the rise and run are equal unless we have a scale that tells us so. With this scale, which is equal along the t and y axis, the slope of the line is 1. We have a rise of 80 and a run of 80, so the slope of the line is 80 over 80, which reduces to 1. But with this axis system, we don't have a slope of 1, because with this axis system, the rise is 4 and the run is 40. So with this axis system, the slope of the line is 4 over 40, which is a 1/10. What's the lesson? The lesson is don't jump to conclusions based solely upon the inclination of the line. You need to also consider the scale. Now, one of the things we talked about in previous lessons is that lines that have slopes close to 0 are lines that are also close to being horizontal. What up with that? This line doesn't appear to be the least bit horizontal. That's because we have mismatched scales on our horizontal and vertical axis. If we redrew this graph using equal scales on the two axes, check it out. Now the line does look very close to horizontal. Let's double check that we do have an equal scale on the two axes. Now it takes two tick marks to get from 0 to 20 on the t-axis, so our scale must be 10. That's also the scale on the y-axis, 0, 10, 20. So if you want to talk about the general steepness of a line, you're probably going to get your most accurate representation if you use an equal scale on the two axes. Now I want to talk about the issue of broken scales, which probably isn't what you think I'm going to be talking about. Let's graph the line with the equation P equals 100t plus 100,000. Well, let's begin by giving ourselves some graph paper. Let's also begin by talking about something that there's just no way we're going to be able to do. 100 is pretty far from 0, which would lead one to think that the steepness of this line is pretty close to vertical. If we think it through a little more numerically, a slope of 100 could be reflected as a rise of 100 over a run of 1. No matter what scale I chose to use on my horizontal and vertical axis, if I used an equal scale, the ramification would be when I move right 1 box, I'd move up 100 boxes. Now I'm looking at this sheet of graph paper I have, and I don't know exactly how many boxes I have in the vertical direction, but I do know that it's well short of 100. Now you might be sitting at home working with supersized graph paper. I don't know, but even if you had 100 boxes to rise, I don't think you really want to count 100 boxes. So I don't think we're going to use an equal scale on our two axes. So no matter what scale we end up using, I'm pretty sure that the line that we draw is going to look a little more horizontal than it really would look if we had used equal scale. Now, one option when you're graphing a line is to calculate the two intercepts, plot the two intercepts, and connect the dots. Let's try it that way. First thing we need to decide is which ones are independent variable and which ones are dependent variable. There's three things about this equation that indicate to me that the dependent variable is the capital P and the independent variable is the lowercase t. One of them is the fact that the equation has already been solved for capital P. When you are presented with the equation of a line that has already been solved for one of the variables, it's almost always the case that the variable for which the equation has been solved is the dependent variable. That's one thing telling me capital P is the dependent variable. What are the other two things? Well, when you have a lowercase letter and a capital letter in a linear equation, it is also almost always the case that the capital letter is the dependent variable. The third thing, when we have a lowercase t in an equation, the lowercase t is also almost always the independent variable, because most of the time when you're using oddball letters like capital P and lowercase t, the lowercase t is representing some sort of time variable. So my ordered pairs are coming at me in the form t, comma, p. So let's first talk about what is the p-intercept. The p-intercept is the point that has a t coordinate of 0. I can figure that out with almost no thought at all. 100 times 0 plus 100,000 is 100,000. Remember slope-intercept form? The coefficient on t is the slope, and the constant is the vertical coordinate of the vertical intercept. That would be 100,000 in this case. What is the t-intercept? The t-intercept is the point that we get when we replace p with 0. If we replaced p with 0, we would get the equation 0 equals 100t plus 100,000. So let's solve the equation 0 equals 100t plus 100,000. Subtracting 100,000 from both sides of the equation, we have minus 100,000 equals 100t. Dividing both sides of the equation by 100 leaves us with t on the right and lops off 2 of the zeros on our minus 100,000, leaving us with minus 1,000. So the t-intercept is the point minus 1,000, 0. So when I choose scales for my axes, I need to be able to get to the point minus 1,000, 0 on the t-axis and 0, 100,000 on the p-axis. Since I need to get to the point 0, 100,000 on the p-axis, I think I'm going to draw my t-axis fairly close to the bottom of my grid. Since I need to get to the point minus 1,000, 0 on the t-axis, I think I'm going to draw my p-axis fairly close to the right side of my grid. Here's my t-axis. Here's my p-axis. Let's see if I've got 10 squares available on my p-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. Just barely, I do have 10 squares available on my p-axis. So I'm going to use a scale of 10,000 on my p-axis. 1, 2, 3, 4, 5 makes the 5th tick mark 50,000. 6, 7, 8, 9, 10 makes the 10th tick mark 100,000. Let's see if I can use a scale of 100 on my t-axis. I'll need 10 tick marks in the negative direction. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, I can't make it. So I think that I'm going to use a scale of 200 on my t-axis. So this is 200, this is 400. In the negative direction, minus 400, minus 800, minus 1,200. Let's go ahead and indicate my 2 intercepts. So my horizontal intercept is the point minus 1,000, 0. My vertical intercept is the point 0, 100,000. Getting out the ruler and connecting the dots. I came in a little low there, but still, this is a fairly accurate representation of the line P equals 100t plus 100,000. Let's talk about some places where we wouldn't want to use this representation. Let's suppose that P represents the population of P-town T years after January 1st, 1990. Let's graph the population of P-town from 1/1/1990 to 1/1/2000. All right, since I want to graph the population from 1/1/1990 to 1/1/2000, I think what I'm going to use on my horizontal axis is the number of years since 1990. That means I'm only going to want to go from 0 to 10 on my horizontal axis. My vertical axis needs to be the population. That's the value of P. The value of P is going to rise from 100,000 to 100,000 plus 100 times 10 over our time interval. 100,000 plus 100 times 10 is only 101,000. So I don't need to go much more higher than 100,000 on the vertical axis. Let's go ahead and draw my horizontal axis close to the bottom. And let's go ahead and draw my vertical axis close to the left. My horizontal axis is going to be the number of years since 1990, and my vertical axis is going to be the population of P-town. Do I have enough tick marks to use a scale of 1 in the horizontal direction? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I do. I'll be able to get up to the year 2000. So here's 2, 4, 6, 8, 10. Do I have enough tick marks using a scale of 10,000 to get to 100,000 in the vertical direction? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just barely. I think you know what I'm going to do? I think I'm going to use a scale of 20,000 on my vertical axis. So that would make this 20,000, this 40,000, this 60,000, this 80,000, this 100,000, and this 120,000. When t is 0, p is 100,000. So we have the point 0, 100,000. When t is 10, p is 100 times 10, that's 1,000, added to 100,000. When t is 10, p is 101,000. Look at the scale. The scale on the vertical axis is 20,000. So between 100,000 and 120,000 lies the point 101,000, but it's only 1/20th of the way from this box to this box. So when I plot the point 10, 101,000, I'm almost on the 100,000 line. So when I connect these two dots, check it out. The line segment I get is almost horizontal. Well, I thought that I said a little while ago that a line with a slope of 100 is almost vertical. That's if you use equal scales. I don't even have anything close to equal scales on my two axes. So which is correct? Well, I'll tell you what, in the context of this problem, I think this is the more correct graph because we're talking about P-town adding 1,000 people over 10 years when they started with 100,000 people. That's almost no population growth, which is reflected by our almost horizontal line. Beneath this box, though, is a population graph produced by P-town's Chamber of Commerce. What's up with the scale, and why do you think the Chamber of Commerce chose to use this scale? Well, let's get familiar with this graph here. Let's first note that rather than defining their horizontal axis as some number of years from 1990, they've just said that the leftmost point is 1990 and the rightmost point is 2000. This is very common in publications when you have years on your horizontal axis. Let's notice on the vertical axis this funny looking symbol here. This is telling us that there is a break in the scale. This is still a vertical coordinate of 0. This point right here is a vertical coordinate of 100. If we maintain that scale, by the time we're up to here, we should be up to 200. We're not even close to 200. We're only up to 100.4. That's what's up with the broken scale. We're using a different scale once we get to the actually indicated numbers than we used to get from the origin to the first indicated number. Why might P-town have used this scale? Because look at the implied slope of the line. It looks very steep, which makes you think that the population was growing very rapidly. We know that's not true because when we used a more reasonable scale, we saw that the population grew almost not at all. By using this broken scale that's showing so few points on the vertical axis, P-Town is creating an illusion that the population is growing rapidly when in fact it's not. So in summary, what my part of the lesson was all about was the importance of scale.